Yeah, so thank you to the organizers for having me. I think this talk will actually dovetail very well with the previous one. I'm also going to be trying to make non-perturbative progress on thinking about metallic systems, although unlike the previous talk, I'm going to completely get rid of quasi-particles and make the interactions very, very big. Okay, so this is going to be based on a couple of recent papers with three amazing collaborators. Darius Shi, who's a fabulous student who I think many of you will be tearing each other apart over trying to hire him as a postdoc someday. Dominic Else, who many of you know, and this other guy. Okay, so many of us are, well, I think all of us are familiar with the great achievement that is the Landau theory of Fermi liquids, which has demonstrated for us that most conventional metals in nature can be described in terms of Fermi surfaces with stable quasi-particle excitations, like shown here schematically. This little E here is my quasi-particle. But there are many materials in nature which defy the predictions of Landau Fermi liquid theory, and we call them non-Fermi liquids, and those are going to be really the main focus of this talk. In particular, one central example that many of us have been fixated on is the so-called strange metal, which is a type of phase that appears in many, many materials, ranging from, say, cuprates to much more recently twisted bilayer graphene. And we generally characterize the strange metal as a state where you have T-linear resistivity over a very, very large temperature range, very high temperatures all the way down to very, very low ones, which is in contrast to an ordinary metal, for example, which at low temperatures should see a T-squared resistivity. And again, this just emphasizes the sheer number of materials here that display strange metal behavior. Cuprates, which we haven't heard as much about in this conference, but heavy fermion materials and the types of quantum critical states that we heard about yesterday and the day before, pnictides, moire materials, and so on. And I also should emphasize that there's a lot of phenomenology that comes with the strange metal beyond T-linear resistivity that's also mysterious, that we have no real explanation for. So in some materials, we observe bilinear magnetoresistance. There's an old mystery having to do with the temperature scaling of the Hall angle as well. How do we explain that the cotangent of the Hall angle in some strange metals scales like T-squared while the resistivity is T-linear, and a great many other phenomenological aspects that I don't have time to do justice to in this talk. Okay, so to explain the family of around strange metals, we really cannot leverage a quasi-particle picture. And so we have to get rid of the quasi-particles somehow. And as theorists, this then leaves us with a very unsavory kind of problem, one where if I take my Fermi surface and excite a quasi-particle, it's going to want to scatter at all energy scales. It's just completely unstable. And now we're faced then with a problem of extremely strongly interacting infinite number of gapless degrees of freedom. This is one of the hardest problems that we can think of in many body physics. And as a result, as the experiments in this field continue to grow tremendously and we encounter many, many more mysteries, our theoretical understanding lags tremendously behind. So the main goal of this talk is then to be trying to develop general principles for non-Fermi liquid states, using notions of emergent symmetries and anomalies in particular, which I'll get to what that means in a bit, but I hope that that type of technology will also be somewhat inspirational for those of us in this room who are also interested in, for example, trying to understand metallic states where there's an interplay of topology and interactions like what we were hearing about yesterday. And my main philosophy, though, broadly speaking, for attacking these problems is to really try to start with some unifying observable feature, and also what models we do know. There are probably a great many more models. There are unknown unknowns in this case, but there are only so many that I do know as a theorist. and try to work our way towards general principles from there. I also should note that for the purposes of this talk, I'm going to be focusing on clean systems. I realize that many folks emphasize the role of disorder in strange metals, but I view the clean case as a very nice phenomenologically motivated starting point. I say phenomenologically motivated because there is a fair deal of evidence, at least, that disorder does not influence some aspects of the T-linear resistivity. For example, there are experiments in a wide variety of Coop rates which indicate that the slope of the T-linear resistivity does not really vary much between very, very different materials. And so that suggests that disorder, which should vary wildly between these different examples, at least is not playing a central role in determining the universal aspects of T-linear. So I'm going to neglect disorder for the purposes of this talk. All right, so what is the sharp phenomenologically motivated question that I want to ask in this talk? Well, I'm going to ask whether a clean metal can exhibit what I'm going to call quantum critical transport, which I'll define on the next slide. And I'm going to show that actually for a very large family of simple but extremely strongly interacting models that many of us are familiar with, that actually I can answer this question totally non-perturbatively. All right. So what do I mean by quantum critical transport? So one unifying feature of many strange metals in nature, also non-Fermi liquids more broadly, is scaling behavior in the optical conductivity. So I've shown two examples here, one in the heavy fermion material, ytterbium, rhodium-2, silicon-2, and bismuth 2212, a Coop rate, where if you measure the optical conductivity as a function of frequency and temperature, you see that there's actually a scaling collapse to a function which involves the ratio here of frequency to temperature. So this is, you can see this in both of these very, very nice scaling collapses here, especially this one is really very convincing. So oftentimes as theorists will say, okay, if I have scaling behavior, then there must be some interesting universal feature of the ground state, or what I call the IR fixed point. And unfortunately, though, rather embarrassingly, we don't know of any clean models that of metals without quasi-particles that display this feature. So I want to try to make progress on this question. And remarkably, I can do that. And it turns out, as I said a couple slides ago, that I will be able to develop exact constraints on a wide variety of theories on the optical conductivity. Okay, and this wide variety of theories involve metals near quantum critical points. So the basic setup of this model is something that was developed by Hertz-Millis many years ago. You take a Fermi surface coupled to a boson, which is viewed as the order parameter of some symmetry, which is sitting at a quantum critical point. So you have a phase diagram that roughly looks like this for the boson. You have some disordered state in this tune parameter, which I'm calling R here. At a quantum critical point, I transition to a ordered state, and this boson couples to the fermions on a Fermi surface via a Yukawa interaction with some profile G of K is the fermion momentum and Q is the boson momentum. Okay, and as a result of coupling to a gapless boson at criticality, I can very efficiently kill quasi-particles. Okay, because this boson is strongly fluctuating at all energy scales. My fermions, I just excite them and they immediately want to scatter off of the boson. And remarkably, even though this is some extremely simple model, this is the most naive type of model of a metallic quantum critical point I might try to write down. Turns out that the lower energy fixed point of this theory is still a total mystery. Not total, I will show what we can learn about it, but really up until this point, it's total mystery. And extracting the in particular observable properties like the low temperature transport has been a huge challenge in studying these theories. Okay, so What do I mean, just briefly, by we don't understand the IR fixed point? So I'm going to just try to play a perturbative game to try to understand what the low energy properties of this theory are. So say I consider the two-dimensional case. So I can just do scaling and see that there's actually no small parameter in this theory. So this coupling constant here is going to be relevant by scaling. And I'm going to start my life at some scale where there's this Hertz-Millis effective theory here is valid. And so I'm just going to do something like RPA. I'm going to calculate in perturbation theory my one-loop diagrams and see that the single particle scattering rate that I get from coupling to the boson scales as omega to the 2/3. And what this tells me, because this power 2/3 is much smaller than, it's smaller than 1, is that there's going to be some scale below which quasi-particles get killed off very, very quickly. And as a consequence of having this omega to the 2/3 single particle scattering rate, if I just calculate what the fermion propagator is and I try to be very systematic about it, so I do say large N or RPA, if I resum this back to the fermion propagator, I get a ratio of the scattering rate, omega to 2/3 divided by N, which I need to take large in order for my perturbation theory to be controlled. But then if I try to take the low frequency limit to go to low and lower energies, then actually what ends up happening is that, well, this thing will dominate, N goes up to the numerator. And so then if I try and calculate subleading corrections in perturbation theory, I'm just going to get an explosion of horrible diagrams. This N enhancement will kill off all of the 1/n suppressions that I would pick up in perturbation theory. I just sum order 1 numbers, and life is very hard. So since this property was discovered, there's been a lot of emphasis on improving perturbative techniques to try to tackle these models, but very little in way of general insight. And in particular, transport is still a very, very open direction. All right. So rather than taking the approach of perturbation theory, I'm going to take a rather different approach where I try to make as many judgments as I can, starting from this scale at which this Hertz-Millis effective field theory is valid, all the way down to the infrared fixed point, assuming one exists. So I'm just going to completely try and go around any kind of perturbative calculation using general principles. And our main tool is going to be an emergent symmetry and anomaly structure, which is common to compressible phases. All right. So just as a brief advertisement of what the ultimate result is, our main non-perturbative result is that actually at the IR fixed point of this theory, the optical conductivity actually just takes a very simple Drude form with no other correction. So there's no actually interesting optical conductivity scaling in these theories. And what's really remarkable actually is we can calculate the Drude weight in these theories exactly in terms of properties of the theory at this quantities of this theory at this mid-IR scale. Okay. And so the main physical message then is that alone, at least in these Hertz-Millis theories, critical fluctuations do not generate quantum critical conductivity, which will ultimately then lead us to a question of, okay, how do we actually generate quantum critical conductivity? And the technology that we use will actually be able to guide us toward making progress on that question. All right. And another way of thinking about this is that there's sort of a no-go theorem that we've proven for these Hertz-Millis theories. All right. So now for a bit more technical details. So I'm going to, as I said, start with an effective theory that's this metallic quantum critical point at some scale of lambda mid-IR, which I'm just going to park at some scale, say below that of the microscopic theory, where I've thrown out certain operators which I'm going to deem irrelevant. And I'm also going to perform a slicing of the Fermi surface into individual small patches, where I only treat scattering within an individual patch of some width, which I'm calling lambda patch here. And I can actually take the width of these patches to be anything I want, and I can take it to vary along the Fermi surface, but for simplicity, I'm going to take this lambda patch to be the same in each patch. So the structure of this theory then is going to be a sum of actions on each individual patch, plus an action for the boson, which I'm going to allow to be exchanged between patches, but not scattered between different adjacent patches. So I'll explain in a little bit more detail what that means in the next slide. So the first set of terms, these individual patch actions for the fermions, are going to be just the standard linearized action for Fermi surface. So these psi thetas are just the excitations at some patch, which I'm labeling with a discrete index theta. And I have a linear dispersion perpendicular to the Fermi surface and a quadratic dispersion along the Fermi surface. And I'm going to say that the quadratic component perpendicular to the Fermi surface is irrelevant by scaling, so I'm only going to have what we call the curvature of the Fermi surface here. Okay. Oh, and these W's are unit normals of the Fermi surface. And then the next term here is going to be the Yukawa interaction with some form factor that I'm going to define as g of theta here. And finally, my boson action is just standard Landau-Ginzburg theory. I'm going to pick a regularization for the rest of the talk where this, the critical tuning, so the location of the quantum critical point is just this RC equals 0. All right. So I mentioned a bit earlier that I will allow exchange of bosons between different patches, but I'm not going to allow scattering of fermions between adjacent patches. So what I mean by that is that I can't, as long as I don't have a fermion in, say, patch theta, hop to an adjacent patch theta prime by emitting a boson, that's fine. So I can allow any process where this guy, say, emits a boson with finite frequency but zero momentum and then is absorbed in this other patch such that the fermion over here doesn't hop outside of the patch. Okay, so in other words, for experts in the room, this means I'm prohibiting large angle scattering. Okay. So I mentioned that this family of models is very, very general, and the generality is encoded in this form factor g of theta. So for example, the Ising nematic theory, which you might think of as tuning a Pomeranchuk instability for the Fermi surface, as I go from the disordered state for the boson to the ordered state, just corresponds to a particular example where this g of theta is even across the Fermi surface. I can also consider a case where it's odd across the Fermi surface. So this would correspond to what often gets referred to as loop current order parameter, similar to what Chandravarma has proposed in the context of the cuprates, schematically drawn here. So the important thing is that this guy is odd under inversions. And as a subset of that, I can consider cases where the boson is a U1 gauge field, like what happens for a spin-on Fermi surface, or in the case of the HLR state, the composite Fermi liquid. And that's a particular choice of this g of theta such that it tracks the Fermi velocity. Okay. So the main tools, as I already said, that we're going to use to attack these theories are emergent symmetries and anomalies. So what do I mean by an anomaly, just for us all to be on the same page? Well, I'm going to define an anomaly just as a conservation law that gets broken in the presence of an external field. So say in the absence of external fields, I have some continuity equation, and then when I turn on the external fields, the right-hand side gets broken by some quantity, which is actually a topological invariant. Okay. And actually, the previous talk already did a great deal of work for me, but a simple example of this is the free Fermi wire. So if I just consider a 1D system of fermions at finite density near each Fermi point, I might think that I have conservation of fermion number at each individual Fermi point. But then if I turn on an electric field, of course, I'm going to drive a current. And so I'm going to get more fermions, say, to the right than to the left. And this leads to a breaking of the individual conservation laws at the two individual Fermi points, as shown here. And actually, this can be used, for example, to compute the Drude weight of free Fermi wire. Okay, so I'm going to just extend this 1D intuition to the Fermi surface case. And remarkably, actually, that can take me a very, very long way. So I'm going to start with this mid-IR theory. And notice that actually at each individual patch, it looks like I have a 1D chiral fermion almost, okay, up to this quadratic piece of dispersion that's along the Fermi surface. And so this suggests a very big emergent symmetry which resembles the 1D conservation of left or right movers that we encountered on the previous slide. So at each individual point on the Fermi surface, it might look like I have a conservation of each n of theta. But if I were to turn on an electric field, this should get broken because I need to drive a current. And actually, the conservation law ends up looking like this. And actually, the big insight that we're going to leverage is that, recall the boson coupled to psi dagger psi, but psi dagger psi is essentially the chiral density. So that suggests that the boson is just going to couple like an electric field, and it's going to enter the anomaly too. So now, in this Hertz-Millis effective theory, I have an anomaly which depends on both the background electric field perpendicular to the Fermi surface and the emergent electric field associated, quote unquote, emergent electric field associated with the order parameter. All right. So this anomaly gives us an exact relation between correlators of this phi field, and say I look at q equals 0, so I kill off spatial derivative terms, and this n of theta. And so we can use it as a tool to constrain correlation functions that involve n of theta. So, simple example, I'm going to set q equal to 0, as I already said. And notice that the anomaly equation then simplifies to this nice form here. But I'm going to notice that the equation of motion for the boson is extremely simple. Okay? It just involves this linear combination on the right-hand side of psi dagger theta, psi theta. So I can just take this left-hand side, peel off the time derivatives, and plug it into the right-hand side. And then I just get an equation of motion, essentially for a free boson, q equals 0, where I have this pi AB thing here, which is I just can compute in terms of properties of my original theory. And this tells me exactly what the boson propagator is, at least at q equals 0. So indeed, I can just invert that equation and get that my boson propagator takes this very simple form here, where this pi I can just read off as the boson self-energy is just an exact number, which is a constant. There's no frequency dependence to this. And this result actually turns out to be valid at all scales below the scale of this mid-IR patch theory. So I should emphasize that this then means that there's no interesting non-trivial frequency scaling. They can only come from corrections to scaling. If I add irrelevant operators back into my mid-IR theory, then I can get additional structure here. But otherwise, if I'm sitting right at the IR fixed point, there's nothing. Okay, and this is consistent with perturbative expectations. If you really attack this problem in RPA very seriously, you'll find that any scaling that you would get would come from irrelevant operators. All right. So I can also, just by extending this argument a little bit, get an exact result for the optical conductivity. And just from the Kubo formula, knowing the boson propagator, I can calculate sigma of omega. So actually, just from the anomaly alone, you get this exact relation here And then we're going to immediately use this result from the previous slide, plug it in for G phi phi on the right-hand side, and get this answer here. So because this thing did not depend on frequency, all you get is a simple Drude form for the optical conductivity. Now, for each individual case that I mentioned, each individual type of order parameter, this coefficient here, this Drude weight, will vary. So for example, for Ising pneumatic, this correction term here will be 0, and so you just get a Drude weight for a free Fermi gas. For the loop current order parameters, this delta D here, this correction, takes some intermediate values, so you get a correction due to the coupling of the boson. And for the gauge field case, so this HLR-like example, you just get that this total right-hand side vanishes. So again, critical fluctuations do not generate quantum critical conductivity in Hertz-Millis theories. And I really do want to emphasize that it's really amazing that this type of result is possible in such strongly interacting theories, where we thought nothing, no, almost nothing is known. All right, so I'm beating this a little bit, but again, what we've learned is that these types of emergent symmetry and anomaly tools are very useful in constraining even these very strongly interacting theories with no quasi-particles. And for these Hertz-Millis theories, we can just get exact answers. Okay, for at least pi of omega, the boson self-energy, and the optical conductivity. Okay. So in my epsilon amount of time I have left, I want to revisit this question we asked at the beginning of can a clean metal exhibit quantum critical transport. Well, it turned out that we called our paper gifts from anomalies. We had too many gifts, and we need to get fewer gifts. Okay, we need to break some anomaly constraints. So there's a simple way of doing that. In the original setup of Hertz-Millis, we had a boson field which coupled to essentially a conserved density, the psi dagger psi. And that essentially gave us this nice connection between the equation of motion and the anomaly equation, which allowed us to more or less solve for the boson propagator. But if I change this a little bit, I have a boson which mixes two different fermion species. So say I have two different Fermi surfaces now, one associated with psi and one associated with a new field chi, where the boson couples between them. Now I can couple the boson to some non-conserved fermion bilinear, or some linear combination of them, and not get these kind of constraints. Okay, get a relaxation of the constraints. So there are a couple of simple types of models where this type of physics plays out. One, many of us in this room, especially who've worked on heavy fermions, are familiar with, which is Kondo breakdown. But another one, which I'll focus on the next slide very briefly, is a model which has been in vogue recently, which is something that people refer to as Yukawa SYK. All right, so what is the Yukawa SYK model? You basically take this Yukawa type interaction here with n fermion species and n boson species and couple them to some with some coupling constant, which is random in the flavor space. And it turns out that using anomaly arguments, we can calculate using an anomaly-assisted large N approach the optical conductivity in this theory and find that you do get quantum critical scaling. However, this model has a number of issues that we can actually sort of see from this immediately. So the n equals 1, this should reduce back to the original Hertz-Millis type theory that we were already describing. But we know that that theory cannot have interesting optical conductivity scaling. So that means that there's going to be some issue with continuing n to 1 and omega to be small and some tension in orders of limits. And indeed, that's what we ended up finding here. So while we did find an interesting fixed point, which has omega to the minus 2/3 scaling here, there's still a lot of important work to be done. And so with that, I want to repeat my mantra of general principles are very useful. You know, these constructs of symmetries and emergent symmetries and anomalies constitute an organizing framework that can be helpful both in this kind of problem and much more broadly in strongly interacting compressible theories. And we hope to be able to leverage this strategy of adopting general principles beyond just these Hertz-Millis type theories, looking to, say, Kondo breakdown models and beyond, and stay tuned for that. I think we've made some interesting progress there. And also to attack other interesting types of transport where there's still many enduring mysteries. In particular, magnetotransport is something that's been near and dear to me and that I hope that we can make some good progress on. So with that, yeah, please ask away questions.
Thanks a lot for the nice talk. So where does the Kondo lattice fit in? So these anomalies violated somehow or not?
So
particularly, I mean, as we know, right, the Kondo lattice can have essentially magnetic instabilities, and
right.
Can you map? Does it at the end still map to Hertz-Millis, or are there things that where some of the things you relied on for the calculation here that break down for the Kondo lattice?
Right. So the Kondo breakdown type story, I guess, if we start with a Kondo lattice type model and try to understand the Kondo breakdown transition, we can write down a attempted and effective theory for that, which is not Hertz-Millis-like. Involves multiple Fermi surfaces, one for neutral spin-on type excitations when you fractionalize the moments, and one for the charged degrees of freedom. And the Kondo breakdown transition then would be described by an order parameter which couples these two Fermi surfaces. And so that fits into this type of picture here. So it's beyond.
To generate terms basically which are beyond
Exactly.
Hertz-Millis.
Exactly. Yeah.
Thanks.
I wonder if the common SYK case suppose Boson or particle is a gauge Boson, then as you said earlier, the duty is vanished.
So I mean, for this Yukawa SYK example, it's not really clear to me what's meant by having the boson be a gauge field. If for this Yukawa SYK type example, it's not really clear to me what's meant by the boson being a gauge field.
Right, but I think in general, suppose the boson is a gauge field, actually as a gauge constraint, I think it is ensure that it will be matched.
Sure, but
I wonder in this case, is there any interesting frequency dependence that you would expect in the
okay, so if I view the generalization of the gauge field case to this Yukawa SYK as just having a GIJK, which is odd under inversions. So it's not really I don't want to say that it's a true gauge field because I'm not gauging any symmetry when I do that because of this complicated trilinear structure. So this GIJK has these three indices and phi is just a vector here. Then sure, I will still get this optical conductivity, but that's because actually when I write down this large N theory, the usual type of shift argument that I would use to say that the conductivity is 0. So if I were to write down a coupling to well, I guess I shouldn't go to the board, but if I write down a coupling to a background field, that coupling will not involve this GIJK, and so I won't be able to, this GIJK still being random, I won't be able to shift phi to get rid of the background probe. So I will still see an optical conductivity even in that case. Maybe we can talk in more detail about this later. It's a bit hard to explain just in words.
Sorry. Is it a necessary assumption that the bosons have like quadratic actions like partial t-square in your theory? Like, is it necessary or?
It's necessary to get the constraint that we get on the boson propagator. But that's a self-consistent assumption in the sense that in the disordered phase, phi4 is irrelevant by scaling. If you could construct a scenario where there are, say, boson self-interactions with just some big anomalous dimension that mean that they're important, then that would change the story, and that would be very interesting.
So
but
sorry, go ahead.
But so far, nobody's been able to construct a model where that actually happens.
I see. So are you saying that if we modify the bosonic part of the theory, maybe there's a chance that the conductivity might not be Drude-like?
Yeah. So if you manage to couple the Fermi surface to a CFT where somehow the influence of that coupling doesn't change the fact that you get big anomalous dimensions on the boson potential, then yeah, you would see new types of effects. So yeah, I think that's a really interesting question and it's worth pursuing.
Is the linear and temperature resistivity included in the form you get for the optical conductivity?
Sorry?
Is the linear resistivity, temperature dependence of the resistivity, implicit in the optical conductivity result you get?
So unfortunately, because all we get is Drude, we don't see anything that, in these Hertz-Millis type theories, we don't see anything.
No, but in the last result.
Oh, in this thing. Good. So, there we go. Okay, so that's a bit of a tricky question. Going to finite temperature in this theory is actually a little bit non-trivial. So, if we try to actually calculate sigma of omega and temperature, there'll be some intermediate temperature regime where hopefully you would see omega over t scaling that, if I tune some parameters in theory, might be t-linear. But actually, because of IR singularity issues, we don't know where that scale happens. So it turns out that thermal fluctuations will dominate in this theory. And that's still actually an open problem that needs to be solved.
Okay, thank you.
I want to ask about the higher dimension anomaly. It's like some generalization of the 1D Carroll anomaly. But it's mainly from the mode that's normal to the Fermi surface. I want to ask, is there any interesting thing come from the mode the tangent to the Fermi surface? Keep parallel square over some curvature, that mode.
So the answer is I don't think so, but one can try and generalize this anomaly to include more interesting nonlinear terms that involve the direction along the Fermi surface. Those can't really be captured in the patch theory. And in principle, if I try to couple the theory to an order parameter in an interesting way, maybe those can do something. But at least in this simplified type of model, they don't do anything. Yeah.
Yes, so in many of your formulas, there is a quantity Vf that appears. What is that Vf in the?
So the Vf that you're referring to is
for example, here
this one.
Yeah.
This is the Fermi velocity.
But are we in the non-Fermi liquid regime where?
So this is the bare Fermi velocity. It's not the bare Fermi velocity. Yeah. So the bare, if I'm sitting at sorry, there's some lag here. There. So this is the value of the Fermi velocity which enters this action at the mid-IR scale.
But I'm not sure I understand the philosophy here. I thought we are going to some IR theory that is complicated,
Sure.
and you are trying to use universal anomaly argument to deal with that, but somehow you still have an input from the UV, right? Somehow it doesn't disappear, isn't it? Is it
So
expected?
there's a perspective from which that's a bit surprising, but I guess what I can say is that, really, okay, in the IR theory, sure, this value of V Fermi is not going to be the true value of V Fermi, but whatever universal number I calculate in terms of this thing still exists at the infrared fixed point. It's just that I no longer should interpret the VF that exists in that equation as the sort of true infrared value of VF.
So yeah, maybe relatedly, if you sit at this mid-IR scale where you can trust this theory, and then you do some RG at that mid-IR scale, but not so down in energy that you lose control of the theory. This universal number depends on the ratio between the G's and the VF.
Yes, that's true.
So is it the case that these renormalize in the same way? Such that that's invariant? Seems like that's a prediction of what you have.
Yeah, I think that's a reason, that's a correct statement.
I see.
Yeah.
Thanks.
So if you go beyond the linear response, imagine that I'm thinking about like nonlinear conductivity. Then from your theory, you would expect that again, even for say other nonlinear conductivity, you wouldn't see any boundary constraint.
If I went beyond linear response. That's an interesting question. Within this framework, I haven't thought too much about nonlinear response. I think, well, yeah, there's some challenges with doing nonlinear response in this framework where I've sort of declared that I'm only interested in like deep infrared properties. And yeah, I'm not sure what the, I don't know if there's some universal feature that actually Sun may know the answer. Within your, so you have a framework where you use Fermi surface bosonization to try to attack a similar problem with a similar type of anomaly. Do you see universal behavior in the nonlinear response? Okay. Yeah, that's probably, yeah. Your framework is probably the right one to attack that problem.
I think